So last time we defined the poincare-birkoff-witt theorem, which states that there's an isomorphism between the symmetric algebra and of the k-module of a G Lie algebra and its associated graded module of its enveloping algebra. And today we're going to be looking at we actually did the entire proof in one video. And so today we're going to be looking at corollaries of the poincare-birkoff-witt theorem. And that is our first one here. So, corollary 1. Let G be a free k-module. I'm going to let W be a sub k-module of Tn. And with this they mean that it's a k-module and a submodule of Tn. And we're going to be referencing some of the functions we defined last time. If the restriction of our taf m to W, which is mapped from our restriction W to the symmetric algebra of component n, is an isomorphism, then the restriction of Cn to W is an isomorphism from W is an isomorphism of W obviously onto a supplement of U to the n minus 1 in U to the n. And a quick reminder of these maps T and C. They were in a diagram which I'm going to see if I can find. So I believe the diagram was we have this map from Tn getting sent to Un. That was our Cn. This map taf n is sending Tn to Sn. And theta n sends it to Gn, the graded. And similarly, omega n sends Sn to Gn. And the idea is that psi and theta are our canonical mappings restricted to their domains that you can see. And that uniquely determines taf and omega. Now the proof of this corollary is that if you take the composition of omega n to the output of Tn and restrict it to W, this is a bijection of W onto G to the N. has is the composition of theta n with Cn. And that is because this diagram commutes. And those are the two ways of getting Tn to Gn. And that's actually it, because, yeah. Second corollary. If G is a free K module, the canonical mapping of G onto its enveloping algebra is injective. And the proof is corollary 1 taking W to be T1 inside of T. Now, quick note, when G is a free K module, especially when K is actually a field, G is identified with a submodule of U. The definition and how that works is from the above corollary. And so in this context, we're just going to be assuming this a lot of the time. Just kind of referring to elements of G inside of U, and you can see how that works out. If G admits a totally ordered basis as always, x lambda, lambda is indexed by big lambda. The elements of the form x lambda I, where this sequence of lambda I from 1 to n is an arbitrary increasing finite sequence of elements of our indexing set. Oh, sorry, this is not the collection of these elements, this is every possible product of x lambda I. And these form a basis of U as a K module. And let's look at the proof of this one. We're going to let big lambda n be the set of increasing sequences of n elements inside lambda for some some m inside lambda n. We're going to let y of m be formed from these xm as you would expect. Going to let, in this case, w be the submodule of Tn, essentially with basis ym for m in lambda n, so consisting of n elements. Now, by corollary 1, the restriction of Cn, which is from T to U, to W, which is a map from W, is an isomorphism of W onto a supplement of U to the n minus 1 in UN. As Cn of ym just multiplies the components of ym together, we are done. That is our next corollary. There are, I believe there's 7 of them total. Just so you can kind of keep track of where we are in space, because that's what this is just going to be, going through all 7 corollaries. Speaking of which, corollary 4. We're going to find S prime to the n be a subset of Tn consisting, that is unreadable, be the homogeneous symmetric tensors of order n. We're going to suppose that K is a field of charge 0. Then the composite mapping, I'm just going to write here as canonical composite, S to the n to S prime to the n to un, where each of these maps are just the canonical maps, is actually an isomorphism of Sn onto, as always, a supplement of u to the n minus 1 in un. Once again, this is just an example of corollary 1, where we set w to be this s prime n. Now, going forwards here, what they call henceforth, I cannot spell forwards apparently. K is a field of characteristic 0. We're going to let eta n be the map of Sn to un, like the one that filters through S prime n and maps onto a supplement of the un minus 1 below. And we're going to define u, this super n, be eta n of s to the n. So that u's vector space is the sum of these u to the n. We see that these etas define an isomorphism of S onto U which, and these are both sums. This is called the canonical isomorphism of S onto U. And I should have noted before this is a vector space. Isomorphism, and very much not an algebra isomorphism. So our bracket essentially is not guaranteed to carry over. But the rest of the algebra, which is just a vector space, is. Now I need to draw a diagram here, so I'm going to get a new page. And so I don't need to write that big, but we have this map, this S prime n, which each Cn is going to send to U to the n. And TAF is going to send it to TAF n, which is going to send this S super n, which eta sends back up. I'm going to our graded n. We get this map being called theta n, and this map being omega n, and this whole thing commutes. And with each of these maps a vector space isomorphism. Now, for a sequence of elements x to the I from 1 to n in our original Lie algebra group G, remember Lie algebras? It's exciting. Then eta n maps the product of xi's in S to this element 1 over n factorial times the sum of sigma in the symmetric group of order n of the product of x sigma I. So essentially we're multiplying them in every possible order, adding all those possible orders up, and then dividing with a number of orders. And this is going to be in U, as you can see. Now, time for corollary 5. Corollary 5. Let H in G be a subalgebra with enveloping algebra of U. Suppose that H and G of H are free as K modules. Now, going to let X alpha, where alpha is indexed by the set L, be a basis of our H, and Y beta, indexed by our set M, could be elements of G whose canonical images form a basis of G over H. So we essentially have a basis of H and G over H, except they're all inside of G actually. We don't need to do any additional work to get that for the XA, but for the Y we're taking representatives. So here's our consequence. Here's our corollary here. Two parts. The canonical homomorphism of U prime, the enveloping algebra of H, I did not write the prime up there, into the universal algebra of G is injective. B. If the indexing set of G over H, of the pre-basis of G over H, pre-base is probably not the right word, is totally ordered. Then the elements spelling the is the first step. Consisting of the product of y beta I, where beta is an ascending sequence, from a basis of u considered as a left or right, of course, module. That is bad even by my standards. Module of u prime. Where is our proof? So we're going to order the union of L and M, our two indexing sets, such that I'm just going to write it like this. L is less than M component Y, so every element in L is less than every element in M. Then the elements, the products X alpha I of course, ascending alpha I and this product is calculated in u prime form a basis of u prime. And that was corollary 3. The elements of the form, the product of x a to the I times the product of y beta to the j in U, once again of ascending sequences, form a basis of U. Hence, the canonical homomorphism from U prime into U maps the elements of a basis of U prime to linearly independent elements of U, and so is injective. We also can see that these y beta I of ascending beta I form a basis of U as a, we went with left, U prime module, And so for it to be a right U module, you just have to order L union M such that L is greater than M. And that is everything. So from this, U prime is identified with, I'll try to avoid too much shorthand, the subalgebra of U generated by H, and this identification is through the canonical homomorphism U prime into U. Alright. So, with that, we've got 5 down, 2 to go. Corollary 6. Suppose the K module G is the direct sum of n algebras of form GI, with each being a free K module. We're going to let a bunch of UIs be enveloping algebras of each GI. We're also going to let theta be the K-linear mapping of the K-tensor from 1 to n of these enveloping algebras into U, defined by the multilinear mapping of the list of elements UN to their product, and this map is going from the product of these UN of UI. I did not use the index in this one either. UI into U. Then this map phi is a K module isomorphism. So we're going to let x lambda I for lambda in an indexing set be a basis of GI. I'm going to totally order the union of these Li such that each Li is greater than the indexes of Lj for I is greater than j. So essentially index them in order. Then the elements consisting of the tensor product how am I even going to write this? I'm not gonna bother doing a fancy notation. It's x1 lambda 1 through x1 lambda say p, and this is going to be tensored with the next one all the way through to the x to the n. We're going to say new 1 multiplied all the way through to x to the n new q with lambda 1 less than or equal to all the way through lambda p. This is going to transfer over each set all the way up to new q. This constitutes a basis of our tensor product of in K of all these UIs, all these universal algebras. And phi maps each such element to the product of each x to the something to an index to a different index, which is a basis of u. That gives us what we want. Notation gets kind of messy, but overall I think that's pretty intuitive as before. And this leaves us with, as promised, one last corollary, going to be a bit of a simpler one, and then there's one more topic. Yeah, no, we'll leave that for later. Okay, corollary 7. If K is an integral domain, I'm gonna have to look up what that means. I don't remember any of like the specific small group ring theory terms. And G is a free K module, then its universal algebra U has no zero divisors. So I'm guessing, I will double check, because I need to rest my hands anyways, but I'm pretty sure an integral domain just has no zero divisors. because that's kind of how these ideas just tend to get transferred over by these corollaries anyways. Yeah. There's no zero divisors, that is, the product of two non-zero elements is non-zero, as you would hope. The proof of this is pretty straightforward. G is isomorphic to a polynomial algebra over K. That was the very first theorem we proved. Consequence. And polynomial algebras are always integral domains, I'm pretty sure. Integral domain. And that is pretty complicated proof, I know, but that will be it for today. I think we have one more topic, two more topics, but probably going to be one more video from this area, and then we're going to switch over our text here to get kind of a jump. I think it's also a discussion of the universal algebras. It is, yeah, it is, but it's going to be a shorter one. And for better and for worse, it's going to be a lot denser, but it's going to be, that hopefully might make it a bit easier to follow. But yeah, so we're going to kind of go over all this again, very much from a different perspective, which hopefully should help us out, actually. But that's not going to be for a couple videos at least.